Our next question, what is the oxidation number of manganese in KMnO4 and MnO4 minus? In this question, to calculate the oxidation number, you should know what is the meaning of an oxidation number. Oxidation number is the apparent charge of an atom, and the rules say that the sum of oxidation number is equal to 0 when it comes to a compound. When you get a species like this, MnO4 minus, the rule says that the sum of oxidation number is equal to the charge possessed by it. Therefore, now if I want to calculate the oxidation number of manganese in KMnO4, it is understood that alkali metals, lithium, sodium, potassium, these are designated as +1. I want to calculate for manganese, I will take it as X. Oxygen, it is designated as -2. Exceptional cases in peroxides, it is taken as -1. Therefore, if I try to calculate what is the oxidation number of manganese in KMnO4, it is 1 plus X plus 4 times -2. I mentioned the rule, sum of the oxidation number is equal to 0. Therefore, by all means, I will be getting X is equal to +7. Again, what is the oxidation number of manganese in MnO4 minus? The rule says the sum of oxidation number is equal to 0 in a compound, while the sum of oxidation number is equal to the charge possessed by it. For example, in this, I want to calculate the oxidation state of manganese. I write it as X plus 4 times -2 is equal to -1. Again, I get X is equal to +7. Therefore, the correct answer for this particular question, oxidation state of manganese in KMnO4 and MnO4 minus, is +7 and +7. Therefore, option A is the right answer. Our next question, what is the oxidation state of sulfur in H2SO5? You have heard about sulfuric acid, H2SO4. H2SO5 happens to be Carr's acid, peroxomonosulfuric acid. This is an exceptional case. As a little while ago, as I was telling, sum of oxidation number should be equal to 0. That cannot be applied here because of the presence of peroxy linkage. By all probability, if you use the method that I have taught you, you will be getting the answer as +8. How do you get +8? 1 into 2 plus X plus 5 into -2, you get X is equal to 8. But we know that the maximum oxidation state of sulfur is +6. Therefore, this is an exceptional case. Oxidation state of sulfur in Carr's acid happens to be +6, and the right answer is option A, +6 is the answer. Along with this, there are a few more exceptional cases. Like you would have heard about Marshall's acid, H2S2O8. Even in that, if you do by the conventional method, you will get the oxidation state of sulfur to be greater than 7. But even in Marshall's acid, oxidation state of sulfur happens to be +6. Reason for that is because of peroxy linkage. While calculating oxidation state should be taken as -1 in one of these steps. Like that, one more exceptional case, CrO5. If you happen to work it out, you get CrO5, X 5 times -2 is equal to 0, X would be equal to 10, but chromium cannot have an oxidation state as plus 10. In chromium also, oxidation state of chromium happens to be for CrO5 is plus 6. Therefore, remember 3 exceptional cases. Oxidation state of sulfur in Carnot's acid is plus 6. Oxidation state of sulfur in Marshall's acid is plus 6. Oxidation state of chromium in CrO5 also happens to be plus 6. We will move on to the next question. The oxidation number of X, Y and Z are plus 2, plus 5 and minus 2. Which of the compound is holding all these oxidation state? Now you know the general rule, sum of oxidation number is equal to 0. Let's see by substituting the value of X, Y and Z which matches to it. If I happen to substitute X is equal to 2, 2 plus 5, 7, 7 minus 2 happens to be 5. This may not be the right option. Hope you are getting the answer now. Start working on, let me work it out. 2 into 2 happens to be 4, again plus I have Y, that is 5, minus 2 into 3, minus 2 into 3, minus 6, minus 6 plus 5, minus 6 plus 5 is 1, 1 into 2, again I don't think I am getting 0 here. So even this cannot be the right option. We will go on to again option C. We will work it out. X 2, 2 into 3, 2 into 3 is 6 plus, I will work it out together now, Z 4 times minus 2 into 4 minus 8, minus 8 plus 5, minus 8 plus 5 happens to be minus 3, minus 3 multiplied twice, therefore 6 minus 6, I am getting 0 here. Therefore, the right option is option C, X3 YZ4 twice. Our next question, which of the following oxides cannot act as a reducing agent? A clue to solve this question would be, the first non-metal that you have, try to calculate the oxidation state of it. After calculating, find if it attained its maximum state. That will help you in predicting whether it can act as a reducing agent or not. Let me help you. SO2 in this sulfur, X plus 2 times minus 2, I get sulfur is equal to 4. I know that sulfur maximum oxidation state, all this while I was telling, is plus 6. It has a tendency to again go to plus 6, therefore it can act as a reducing agent in further reactions. Next, NO2, nitrogen dioxide. Again in this, if I happen to work it out, X plus 2 times minus 2 is equal to 0. X will again be equal to 4. We know that nitrogen, the maximum oxidation state of nitrogen is plus 5. It still has a long way to go. It can attain plus 5 oxidation state. It can also act as a reducing agent. Come back to the next one, carbon dioxide, CO2. In CO2, oxidation state of carbon happens to be plus 4 again. In this, carbon maximum oxidation state is plus 4. It has attained its maximum oxidation state is plus 4. It cannot further undergo any changes. Therefore, probably this is the right answer. Option C, carbon dioxide cannot act as a reducing agent. Let's verify again. ClO2, in that chlorine, X 2 times minus 2 is equal to 0. I get again for this chlorine, I get it as 4. But I understand chlorine can attain a maximum oxidation state of plus 7. In all these that you have seen, though the oxidation state is 4 for all the non-metal that you have seen here, but only one which has attained its maximum, which cannot further undergo a change, is CO2. Therefore, carbon dioxide cannot act as a reducing agent. Next question. A reducing agent is a substance which can: option A, accept electrons; option B, accept protons; option C, donate electrons; option D, donate protons. In this, first of all, what is the reducing agent? You know the term called oxidation. Oxidation is a process in which there is loss of electrons or gain in charge. That which undergoes oxidation is arguably the best reducing agent, meaning oxidation, there is loss of electrons, there is gain in charge. That which is undergoing a loss of electrons or gaining in charge can be a very good reducing agent. Keeping these points in mind, let us attempt this. Reducing agent is a substance which can accept electron, accept proton, donate electrons, donate protons. I would say the right option is option C, donate electrons, because it is connecting to my definition of oxidation, process of loss of electrons, gain in charge. Therefore, it can be a very good reducing agent. Right option is option C, donate electrons. In the next question, in the reaction, when white phosphorus is treated with an alkali solution, this method is a method of preparation of phosphine. We get phosphine and sodium hypophosphite. Options: P is only oxidized, P is only reduced. Option C, P is both oxidized and reduced. None of these. This is a classical example of one of the type of a redox reaction. This is an example of a disproportionate reaction. What do you mean by a disproportionate reaction? A disproportionate reaction is that in which the same element in the reaction shows both oxidation as well as reduction. If I happen to calculate what are the relevant changes that are taking place for phosphorus, I know that phosphorus in its elemental state, oxidation state of it is regarded as 0. If I try to calculate what is the oxidation state of phosphorus in phosphine, I get it as X. 3 into 1 is equal to 0. I get phosphorus is equal to -3. Similarly, if I try to calculate what is the oxidation state of phosphorus in sodium hypophosphite, I get it as oxidation state of it would be +1. Now, as I look into this example once again, 0 is becoming -3, decrease in oxidation number. 0 is becoming +1, increase in oxidation number. That means phosphorus is both oxidized as well as reduced. This is an example of disproportionate reaction where the same element undergoes oxidation as well as reduction. Therefore, the right option is option C, P is both oxidized and reduced. Next question, which of the following is not a redox reaction? There are different categories of redox reaction. One is combination, another one is decomposition, another one is metal displacement. In this, I don't have a combination example, but you know that Na plus Cl2 can give NaCl. It is an example of a redox reaction again. In this that I have option A, B and C are example of decomposition reaction. But how do I identify whether it is a redox reaction or not? In option A that I have, water gives H2 and O2. If we happen to look into option A, B and C, the products that are being formed, one of the product will be in elemental state. Necessary condition for a redox reaction is, for a decomposition redox reaction is, one of the products should be in elemental state. In this I have H2O giving me H2 plus O2, both hydrogen and oxygen are in elemental state. It is a redox reaction. Potassium chlorate undergoes decomposition to form KCl and O2. Oxygen is in the elemental state. It is a redox reaction. Calcium carbonate undergoes decomposition to form CaO and CO2. Either of it is in elemental state, therefore it cannot be a redox reaction. Therefore, I would say option C is the right answer. Calcium carbonate undergoing decomposition to give calcium oxide and carbon dioxide. None of the products are in elemental state, therefore it cannot be a redox reaction. Option D, if I happen to look in, it is an example of a redox reaction by metal displacement method. In the next question, the number of electrons involved in the cell reaction. There are two half cells connected by a salt bridge. Aluminium is at anode, copper is at cathode. The total number of electrons involved in the cell reaction. How do I do it up? Now at anode I have Al giving me Al3 plus. The half cell reaction at anode is Al giving me Al3 plus. I have 3 electrons involved in this step. At cathode, I have copper, Cu2 plus giving me Cu. 2 electrons are involved in this. One of the basic rule when salt bridge is there, connecting to half cell reaction, the number of electrons lost should be equal to the number of electrons gained. I have 3 electrons lost, 2 electrons are gained. To make it equal, I multiply the above equation with 2 and the second equation with 3. Therefore, total number of electrons involved in the transition happens to be 6 electrons. Therefore, the right answer for the number of electrons involved in the cell reaction is 6. Option D is the right answer.